This is what I call a recall slide or a review slide that we had actually in part 1. Here's our atom, general structure of an atom. We said the center is a nucleus, and in the nucleus, the center is a nucleus, and in the nucleus we have protons and we have neutrons. And we actually said protons are what gives the element what identity it is. Under protons, if you want to, we call that the atomic number. Let's see. And then also, well, we talked about electrons. Electrons are in a cloud outside the nucleus. And one of the things about electrons, we talked recently when we talked about valence electrons, is that number of electrons is equal to number of protons if it's neutral, if the atom is neutral. Okay, let's see. I think that's what I want to talk about. The next slide is going to introduce something related to the neutrons. Okay, so the protons tell you what element an atom is. The number of electrons kind of give you charge if there's not the same amount of electrons as protons. And neutrons are important in this way. Neutrons actually, I'll kind of write it here. Neutrons, I'm going to say number can vary. Now, Mother Nature knows what's acceptable with regard to number of neutrons in the nucleus of an atom can vary. But, yeah, I mean, we can't just willy-nilly do it. But Mother Nature's got her thought of how that works. So just to kind of review, so what atom an element is all related to the atomic number, the number of protons in the nucleus of that atom. But the identity of what element an atom is not changed by neutrons that may or may not be in the nucleus of an atom. That's where I said Mother Nature knows what she needs to do. So we basically have these different, we have atoms of the same element, but because they have the same number of protons in their center, but they have different number of neutrons. So one of the things about neutrons is we say that neutrons and protons generally weigh 1 AMU. So since we're changing the number of neutrons in the center of these atoms, they are going to have different masses. And this is one of the things where it's good to show you an example here in a minute. So they will behave the same, but they will weigh differently. So here brings an important concept that if you were to look in the nucleus, so here's my nucleus and here's my electrons out here, okay, electron. If you look in the nucleus and if you count the number of protons and also the number of neutrons, and if you add them together, that will give you what's called the mass number. Now, mass numbers, sometimes students kind of get this a little bit confused. Mass numbers are always integers. They're always whole numbers because you are counting the number of protons and the number of neutrons in the nucleus of an atom. That gives you your mass number. Sometimes those are called nucleons because they're in the nucleus. Makes sense. Okay, so an example would be the element uranium. Of course, the symbol for uranium is U. And we have these two what we call isotopes or isotopic forms of the element. If you were to look up uranium on the periodic table has an atomic number of 92. Atomic number of 92 for uranium. So it has 92 protons. Okay. Now, I want to kind of show you, actually take this as an example for these two different forms of uranium and use this, well, before I leave this, let me make sure we're all on the same page. This 235 and 238, that's what's called the mass number. And the mass number, like I said, is the number of protons, which is going to be 92 in both cases, plus the number of neutrons. Now, here we go. You could run into this sort of problem. So let me go ahead and rewrite uranium. I'm going to have two isotopic forms of uranium. So what scientists generally do is reserve the upper left-hand corner for the mass number. So I'm going to put uranium-235 for that isotope, and 238 for the other isotope. These are two different isotopic forms of uranium. A lot of times then, it's a little bit redundant, we reserve the lower left-hand corner for the atomic number. So I told you that's 92. You can find that off the periodic table. 92 from the periodic table. So if you, let's see, how do I want to do this? This is the mass number, and this is the atomic number. I'm going to go ahead and say number of protons for this, 92, and the mass number is number of protons plus number of neutrons. So I bet you guys buy this, that if I were to ask you how many number of neutrons there are in these two isotopic forms, we can get number of neutrons by taking the mass number and from the mass number subtracting the atomic number. Because the mass number is protons plus neutrons, and the mass number is just protons. So if you take 235 minus 92, you get, and I did this ahead of time, 146 neutrons. Seems like a lot, but all right then. And that's how many neutrons this uranium atom has. For this uranium atom, we can do a similar thing. Take 238 now, and again subtract 92. And I did that on my calculator, and I got 149. Okay. Which makes sense because actually this was 3, the second one was 3 more than the other one. Okay, so that would be 149 neutrons. So now I want you to do one on your own and answer the video question. So here's the thing, I looked up calcium, and calcium actually has naturally occurring 3 isotopic forms. And I'll go ahead in the upper left-hand corner and put the mass number. I got a mass number of 40, a mass number of 42, and a mass number of 44. I even went ahead and looked up calcium, the atomic number for calcium, and I'll put in the lower left-hand corner is 20. So we have 20 protons for each of those. Now, your video question is simply, what is the number of neutrons for each isotope of calcium?